In this lesson, we're going to look at how changing the dimensions of a shape changes the area and the volumes of that shape. We've talked about this with two-dimensional figures, and now we're going to relate it to three-dimensional figures. So I've already gone in and taken these cubes and I found the lateral area, the total area, and the volume for each one of them. And so we'll just fill in the table and kind of see what relationship that we have between the sides, the areas, and the volumes. So if we do the ratio of the corresponding parts, then the ratio of our large cube to our small cube would be 5 over 2. The ratio of our lateral areas is 100 over 16, which reduces to 25 over 4. The ratio of our total areas is 150 over 24, which also reduces to 25 over 4. And the ratio of our volumes is 125 to 8, which does not reduce. So we'll come back to this in a second once we see what the pattern is. If we look at our cylinders, I've already found the lateral total areas and the volumes for the cylinders. I left them in terms of pi so that we don't have to deal with decimals. It's easier because you can just cancel out the pi's and you don't have to deal with those. So I just left them, I didn't multiply the pi out when I was doing the 2 pi r h plus 2 pi r squared. So the ratio of our corresponding parts, it doesn't matter whether you use the heights or the radii, it doesn't matter. I'm going to do small to large, left to right, just to maintain the same as we did up above. So the ratio of our corresponding parts would be 3 over 4, or our heights would be 6 over 8, but again, all of that reduces to 3 over 4. The ratio of our lateral areas is 36 over 64, which reduces to 9/16. The ratio of our total areas would be 54 over 96, which also reduces to 9/16. And the ratios of our volumes is 54 over 128, which reduces to 27 over 64. Notice I didn't use the pi anywhere because 36 pi over 64 pi, those pi's cancel out, and so we can just look at what we have there. Now, what I need you to see, what I want you to see is kind of this relationship is how do we go from sides to area, which these two are together, and then from that to volume. So we always go from sides to area or we go from sides to volume, but everything relates back to what happens to the sides or the corresponding parts. And so if you'll notice that our sides are in meters. They're measured in meters. Our area is measured in meters squared, and our volumes are measured in meters cubed. And this is important because it's going to give you a hint as to what to do when I'm asking about the areas and the volumes, given only the information about what happens to the sides. So because if you'll notice, our sides were 5 over 2. The ratio of the sides was 5 over 2. Well, if you look, the ratio of both of the areas is 5 squared over 2 squared. So whatever happens to the sides, if you square it, that's going to be what happens to the areas. Your volumes, if you'll notice this is 5 cubed and 2 cubed. So whatever happens to the sides, if you cube that, that's what happens to the volumes. Notice we have the same thing here. Our sides were 3/4. Our areas were 3/4 squared, 3 squared and 4 squared, which was 9/16. That happened with both of them. And our volume is 3/4 cubed. 3 cubed is 27, 4 cubed is 64, and that pattern always happens. So if you'll remember the units of measurement, then it will help you to keep up with what you're supposed to do with each of the numbers. So to summarize that, if our corresponding parts have a ratio of A to B, then the ratio of our areas will be A squared to B squared. The same for our total areas. They'll have that same ratio, A squared to B squared. And then the ratio of our volumes will be A cubed to B cubed. Now, everything depends on what happens to the sides. So depending on what you're given, you always want to go back to the sides first and then find the other pieces. So if the ratio of our corresponding parts is 1/3, say they're measured in meters. Don't forget areas in meters squared, whether it's 2-dimensional or 3-dimensional. And then the ratio of our volumes, or the units of measurement for our volumes, is in cubes. So if my sides are 1/3, so say my sides have a ratio of 1:3, then the ratio of my areas will be 1/3 squared, which will be 1/9, and the ratio of my volumes will be 1/3 cubed, which will be 1/27. Okay, now what if I've been given the areas and I want to know what happens to the volumes? You have to go backwards first to find out what happens to your sides. So if this was squared, then you have to think, okay, what would be the square? What squared would give me 36? What squared would give me 49? So if I take the square root of that to go backwards, then that would give me that the ratio of my corresponding parts is 6:7. Then I go from there, and then I can find the ratio of my volumes, because then I need to square or cube. Actually, for volumes you would cube that. So 6 cubed is 216, and 7 cubed is 343. So the ratio of my volumes would be 216/343. Then the last one, we have the ratio of our volumes. Remember, volumes is in units cubed. We have to come back and find this first. Okay, so the first thing was we have to find the ratio of the parts. So the ratio of our parts would be the cubes. So this time you have to think, okay, cube root. So the cube root of 64, and there's a cube root on your calculator. You can go here and go to the math menu, and then you've got your cube root. So the cube root of 64 is 4, and the cube root of 125 is 5. So the ratio of our sides is 4/5, and then from there I can go to the area, and that's 4/5 squared, which is 16/25. Okay, so everything has to come back to what happens to the sides so that you can figure out what happens to all of the other pieces. So let's look at some problems with this. Two prisms are proportional. The height of one prism is 2/3 the height of the other. Okay, this is talking about the sides. If the lateral area of the larger prism is 81 meters squared, what is the lateral area of the other? So if we set this up, we can say, well, if they have a ratio, if there's one is 2/3 the height of the other, then we can say that our sides are in a ratio of 2/3. This would be my small prism, the 2, and the 3 would go with my large prism. Okay, now I need to compare sides, but I want to know about the area. So I want to know the lateral area of, if the lateral area of the smaller one when the lateral area of the large one is 81. You can't compare sides with areas. You have to compare areas with areas. So we need to convert this side ratio into an area ratio so that we can compare them. So if we square them, because area, whatever happens to the sides, if we square that, that's what happens to the areas. So my area ratio should be 4/9. So then we set this up, we cross multiply. So we have 4 times 81. Divide that by 9. And we find out that the other area is 36 meters squared. The area of my smaller one. Okay, so all we have to know, we don't have to know all the pieces to be able to find these areas. So our next one, the lateral areas of two similar cones are 100 pi centimeters squared and 25 pi centimeters squared. The volume is 40 pi centimeters cubed, cubic centimeters. Find the volume of the larger cone. So I have the volume of, I want the volume of my larger cone over the volume of my smaller cone. It doesn't matter what order you put them in. You can flip them over. But whatever you do when you set up your other ratio, set it up the same way. So I did large over small, and so I need to do large over small. Now I have area. I'm asking about volume. So I have to go backwards. So I set up my large, 100 pi, over my small, 25 pi. Those are my area ratios. So I simplify that. 100 over 25 reduces to 4 to 1. That's my side ratio. So I had to go from area, and then I had to go back to sides, so that then I can compare volumes to volumes. Because now I need to cube this to turn it into a volume ratio. So it's 64 to 1. So now I have 64 over 1 equals x over 40 pi, the volume ratio to the volume ratio. Cross multiply, and you get that the volume of the large one then is 64 times 40. I'm not going to worry about the pi. So my large volume is 2,560 pi cubic centimeters, or cc's. If you've ever heard that term, maybe at the doctor with medicine, cc's, that's a cubic centimeter. Okay, 2 cylinders are proportional. If the radius of one cylinder is 1 meter and the radius of the other is 4 meters, then how do the volumes of the cylinders compare? Well, if the radius of one cylinder, remember we compared our parts, so we have 2 different ones. I didn't draw them proportionally, but we can label them. So if the ratio of my parts is 1 to 4, then what is the volumes? Well, this is the ratio of the parts. We have to convert that into volumes. And so my volumes then would be that cubed. So the ratio of my volumes will be 1 to 64. So one of them is 64 times bigger than the other one. Okay, you always have to go back to, it always depends on the sides. If you weren't given the ratio of the sides, then you have to work backwards to that to find either the area or the volume. Number 4, the volumes of 2 proportional prisms are 200 centimeters cubed and 25 centimeters cubed. The lateral area, notice we've got volume, the lateral area is 15. Find the lateral area of the larger. Okay, so again, you were given volumes. So I was given the large volume and the small volume simply because it was written that way. So the large volume to the small volume. Reduce that. Don't forget your calculator can handle that. Math enter. So our volume ratio is 8 to 1. Now remember that has been cubed because volume is cubed. So I need to go to sides. So I went from volume, then I need to go to sides because I can't skip straight to the area. I have to go back to the sides. So my sides would be then the cube root of that. The cube root of 8 is 2. The cube root of 1 is 1. So my sides have a ratio of 2 to 1, which means then that my area will have a ratio of 4 to 1 because I'd square it to get that area ratio. So if my area ratio is 4 to 1, large to small, then the lateral area of the smaller prism is 15. That's the small one. What is the lateral area of the large one? 4 times 15 is 60. And so the lateral area of my larger prism is 60 centimeters squared. Last one. A cone-shaped pile of sand weighs 400 pounds. Now here's the point of this problem is that weight is a volume measurement. So if you are given a problem and it tells you about weight, then what it's talking about is volume. How much does a similarly shaped pile of sand weigh if each dimension is 4 times as large? So we have a pile of sand, and then we have another pile of sand, every dimension about this one. So the sides are multiplied by 4 from these, right? We have our sides. Everything, our sides or our radius, our pieces, our radius, our height, all of those pieces have been multiplied by 4 in our slant height. So then what is going to happen to the weight or the volume of this pile of sand? Well, if our sides have been multiplied by 4, then the area that the sand takes up, then it is going to be times 4 squared, which will be 16 times bigger, and then our volume, or our weight, will be times 4 cubed, which will be 64 times. So the weight of our new pile of sand is going to be 64 times larger than the weight of the original pile of sand. So the biggest thing that you need to remember is kind of go back to this visual of this chart and how things are set up. Everything comes back to our corresponding parts. Then you can square it to get your ratio of your areas and cube it to get your ratio of your volumes, or use square roots and cube roots to work backwards. But this chart right here is the most helpful in remembering how to get back and forth between those pieces.